That's the topic today, and let's get started with beats. And some of you may recall, we are in the topic of waves. We started with traveling wave, and we did waves on a string, which is transverse wave. After that, we spent some time on sound wave. Sound wave is a longitudinal wave. Okay, and then we have gone through the topic of superposition of two waves, and superposition has three applications. What are three applications? Two waves of same omega traveling in the same direction. Interference. In case of interference, the waves, when they interfere, you will have, depending on the path difference, there's a phase difference, and depending on phase difference, there's a amplitude and intensity. Next, we did standing wave. Standing wave, two waves traveling in the opposite direction, two waves of the same frequency, same amplitude. When traveling in the opposite direction, they create a standing wave. And third phenomena is beats. Okay, let's try and understand beats, what way it is different from other two. And beats is a phenomena which is very commonly used in music for the purpose of tuning of musical instruments. Okay, let's see that. Suppose there's a sound source here, and there's a sound source here, and this sound source emits sound of frequency 440 hertz. 440 hertz is a very common frequency used in music, and this is a frequency which is typically used for tuning of musical instrument. Okay, so this is sound source which has a frequency of 440 hertz. So moment we put this sound source on, what would it mean? Moment I put the sound source on, it means it will make air molecules around it to oscillate with same frequency. So if a sound source of frequency 440 hertz is started, it will make air molecules oscillate with the frequency of 440. Okay, that's what happens. And suppose there's an observer here. You can all see an observer here. Okay, you see the face here. Whom does it look like? Does anyone recognize the face? Okay, let it be observer. To me, it looks like Jaideep. See, this thing, it looks like Jaideep, or it could be somebody else. So there's an observer here. What will happen? Even the observer also will hear the sound of frequency 440 hertz. Why would observer hear a sound of 440 hertz, Jaideep?
Due to oscillations of the air molecules which reach
Air molecules. So basically what will happen if we create, suppose we put the sound source on, it will make the air molecule in all the radial direction oscillate in this direction. It will oscillate in the longitudinal direction. So very close to your ears also, you will have air molecules oscillating with the frequency of 40 hertz. So if we plot the motion, assume that we could see the motion of air molecules, we could have seen the air molecules having SHM kind of motion with the frequency of 440. 440 is very quick. It's very difficult to visualize also. Very quickly it will oscillate and it will happen. So what level sound what you hear at this point will depend on oscillation of air molecules at that point. And the sound, it doesn't matter what is happening other places, the sound at a point, what we hear, depends on oscillation of air molecules at that point. So motion of air molecules here, if this oscillates with SHM also, and this air molecules also will oscillate with the frequency of 440 hertz. I don't know what happened to my sound, so why it is not working. It was supposed to create a sound here. Okay, so if we plot this motion, if we plot the motion of air molecule close to the ear, and this is the time, and what we plot on the y-axis is displacement. Which direction? If this is x direction, displacement also happens in the x direction. But to differentiate, write as s. In case of transverse wave, this is as a displacement. So if look the motion of the particle, this is how it will oscillate. And this is one full oscillation. In 1 second, how many such oscillations will get completed? 440 oscillations will get completed. So this is how the motion of a particle close to the observer will look like. What happens if you have switched on only one source? What happens if we switch on the other source as well? This source also we switch on, and this source also has the same frequency of 440 hertz. In that case, what will happen? This source also will create oscillation, and even this oscillation also, if we plot its motion, it will be again a sine function. If I plot same thing, so there are two sources. One is blue source, and other one is a red source, or whatever we call it, a brown source. Red source, let's call it. And if both are equidistant, both sources are identical, it will create identical oscillation. What we notice, the path difference will be zero. So two waves will superimpose. And when we superimpose, what kind of wave will get created? At every single time, we can find the sum of these two oscillations, sum of the two displacement will create this kind of wave. It will create this, which is what we are talking about here. What is this phenomena here? Two waves traveling in the same direction. They reach a common point here. Resultant oscillation is sum of the two oscillations. Assuming that when we calculate oscillation due to first source, we assume the second source to be absent, neglecting the presence of second source. This is a case of constructive interference. It's a case of constructive interference. Both the waves superimpose. Okay. Now, what happens if we slightly change the distance of the source or delay the source? Just go through that again. I hope you understood. Suppose we start moving the source slightly away from the observer. If we start moving the source away from the observer, what will happen? The phase of oscillation here will change. Which phase will change? Red color oscillator phase will change. Just slowly, if you start moving, see this what will happen. If we plot two waves, this waves will happen like this. And if we move the source away by a distance equal to lambda by 2, this is how the two waves will look like. This is oscillation due to first source, and the red one is oscillation due to second source. What is this case about? What does this kind of oscillation indicate? The first one is a constructive interference, and second one is a destructive interference. Okay, so if two sources of same frequency reach O, the resultant oscillation will depend on sum of two oscillation, which depends on phase difference. So what does it mean? At any instance of time, I want to find out what is the resultant oscillation at a particular point. See, all this thing we are concerned only at which particular point. Which point here? The point where the observer is. Let's say this point A. So this oscillation, if I want to find out what is the resultant oscillation, we take at the particular time, we calculate what is the displacement due to first source, what is the displacement due to second source, take the sum of the two. In this particular case, both are always, sum will always come to zero. There will not be any oscillation. This will lead to destructive interference. So what I have talked about is interference. So, but today's topic was beats. But to understand beats, first, again, we go through quickly about interference. Then we look at what way beats is different from interference. Again, let's come back to the same thing. What will happen if second source frequency is slightly different? Earlier, what we had taken, both sources were of the same frequency. Now, if the second source frequency is slightly different, though the amplitude is same, so from here also the source is receiving sounds is coming. So as to the blue source and red source, if they have slightly different frequency, the red source has slightly lower time period or higher frequency. How would the oscillation look like? Let's look at this, and we chose, so when we say, this is the oscillation due to the blue source. Red source frequency is slightly higher. This is how it will look like. Let's see that one, the oscillation due to red source. What do you notice here? Blue source, this is from here to here. If I take this point, this is a crest here, and this is next crest here. What would this time indicate here? What is this time here? It has completed one full oscillation. This indicates time period of the blue source. Inverse of the time period is frequency of the blue source. We have kept these two waves together. What is these two things? Two things are oscillation at point O due to blue source and due to red source. And you see here, this is one crest, and this is the next crest. What is the time? This dimension is time, oscillation. What does this time T2 indicate or TR indicate here? Very easily you can understand here. This time period of red source is slightly smaller, or frequency is slightly larger. So in given time, whatever oscillation blue source completes, red source may complete more number of oscillation. So what we find here, so this is what it utilizes. I hope you understood how the shapes, how the oscillation wave shape differ at point O. Two sources have slight difference in frequency. Which is higher frequency? Red is higher frequency. So in a given time interval, red will complete more number of oscillation, which you can see from the figure. So I kept these two for side by side, and so this is a time difference in one oscillation, oscillation, three oscillation, four oscillation. And what we notice here, okay, this is something by this is what it is. So and now what I'll do now, we'll keep these two waves together. We are superimposing two waves which are slightly different in frequency. Let's keep these two waves together. Put in reverse direction. Let's move these two waves together. So what I have done, we have chosen a time interval t is equal to 0. How I chosen, I have shown it slightly differently, but assume that both waves are together. At this particular time t is equal to 0, both waves are in same phase. Both are at 0 phase. If I draw the phasor of blue color and red color, both color, blue color and red color phasor will look like this. Both are at 0 phase. At this point, okay. And what I notice here, so both are at the 0 phase. By the time we come here, again, this is the point, and we slowly what we notice, this is the point, it has blue has completed one oscillation, it has completed two oscillation, it has completed three oscillation. At this point, the phase of blue is 0, but phase of red is not 0. So at this time, the phase difference is here, the phase difference was 0. Here, phase difference has changed. And as I keep moving, I find phase difference between the two oscillations is gradually increasing. And by the time I come to this particular time here, can you figure out what is the phase difference between two oscillations? Just what is the phase difference?
Sir?
What is the phase difference between two oscillations here?
It will be pi, sir.
Time.
Pi.
They're out of phase.
Yes, sir.
What happened? And phase is changing not with distance. Phase is changing at a particular point with time. Phase is changing with time. Here, it was having constructive interference here. Slowly, this phase delta phi was equal to 0. Phase difference was 0. By the time we come to here, this particular time t here, phase difference has become equal to pi, and this becomes destructive interference. And again, as I keep moving here, at some point we find again we come to constructive interference. So what we understand, I hope this figure is clear. Phase difference, what I observe here, how do we write in terms of a statement? The phase difference will gradually increase from 0 to pi. Hence, the resultant amplitude and intensity. As the phase difference keep increasing, amplitude will keep decreasing, and intensity also will keep decreasing. So both amplitude and intensity will gradually decrease, and it will reach at a state of destructive interference when they stand, and then again afterwards it will start increasing. Here again, so intensity is minimum when phase difference is equal to pi. Afterwards, what will happen? Phase difference will become more than pi, and it will become 3 pi by 2. 3 pi by 2 is equivalent to 3 pi by 2. It may become equal to 3 pi by 2. If it is 3 pi by 2, it will equal to 90 degrees. So anything more than 90 degree. So beyond this point, the phasor will look like this somewhere here. If red is, if blue color is like this, red color would have gained, it would have become something like this. It will become more than 180 degree. More than 180 degree in terms of intensity and amplitude calculation. This angle becomes less than 180 degree. So it is not destructive interference. So from here, constructive. Gradually, it will come to state, if intensity will keep decreasing, come to a minimum, and then again start increasing, again release to constructive interference. This is what will happen if there is a slight difference in frequency. Okay. Dhanshri?
Yes, sir.
Are you listening? Or
Yes,
thinking
sir,
of IP only?
No, sir, I'm listening, sir.
Are you following so far?
Yes, sir, I'm following.
Red color, other color, all clear? Point here. So let's continue further. Okay. So what will happen? So we are talking the case of beats. Two sources, waves traveling in the same direction. And what we had taken, both waves, when they reach here, they create equal amplitude, but the frequency is slightly different. And when the frequency is different, we have chosen initial. So if the frequency is slightly different, phase difference will keep on changing. If omega is same, phase difference remains constant. Frequency is different, omega different. Phase difference will keep on changing. As phase difference keep on changing, resultant amplitude keeps on changing, and resultant intensity keeps on changing with time. Okay, that's what will happen. The phase difference will gradually increase from 0 to pi, and resultant amplitude and intensity will gradually decrease. Decrease till it reaches a state of destructive interference, then again start increasing. That's what we'll observe here. Okay. So, loudness of sound will be maximum when in phase. This is a time where loudness of sound will be maximum and minimum when out of phase. Where somewhere in this time zone, I'll find this will be the minimum loudness and this will be the maximum loudness. And in between, the loudness will keep on decreasing. Okay. Second thing, if you have to observe, it will come. So, and this will keep happening periodically. Periodically means minimum, again maximum will come, again minimum will come. So what will happen? Thus, it will create a sound where intensity is varying periodically. This is an important point. So when two of them interfere, intensity will vary periodically. How does intensity vary? Some of you may recall and think of how does the siren of an ambulance sound. It's a wow, 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 wow kind of thing. So do you know what is happening in that case also? The frequency of sound remains same. It is something like this. Somebody is turning the volume up and down, up and down, up and down. At what frequency? It periodically is being turned up and down. If I turn it down once in a second, it may sound like wow, wow kind of sound. But if I turn the volume up and down with a frequency of say something like 3, it means in 3 times in a second, it reaches maximum and minimum, maximum, minimum. It may sound wow, 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 wow kind of sound. I hope that you all understand here. It creates a sound of varying intensity. And intensity will vary periodically. Anything which varies periodically, we can calculate what will be the time period at which intensity of sound will vary. And if intensity of sound vary, loudness will vary. That's beats. So in case of beats, what an important point we understood. Unlike other cases, it's not constructive interference or destructive interference. It will be phase and phase difference will keep varying. So there'll be constructive interference followed by destructive followed by constructive. And in between, phase difference will keep varying. Hence, amplitude and intensity keep varying periodically. If it is varying periodically, so if two frequencies are given, we can calculate at what periodic interval intensity will vary. Now we are not talking about frequency of sound. So there are two things now: frequency of sound and loudness of sound. Frequency depends on the source, at what frequency the source is oscillating. Loudness depends on other factors also. Loudness depends on intensity. And one of the important parameter intensity is intensity varies as square of amplitude. So this is something what is about beats is about. So the time period for time taken for phase 2 from 0 to next 0. So what we understood from here, this much time it has taken intensity to drop from maxima to minima. And if this time was say something like T naught, again from here it will take similar time T naught to reach to its maxima again. We are not around that point. And this total time will become time period of variation of intensity. This will become time period. So what is the time period of variation of intensity? Time period will be between two. What is the time it takes from one constructive interference to next constructive interference? And what is the time it takes from one maximum loudness to next maximum loudness? That would be time period of intensity varying. Okay, okay, so let's understand here also. See, if I have to calculate here, see, this is the time. See, let's see. See, what is the time here if I mark this point here? Because I'm not taking one time period, I'm taking this point here. What is this? This point is equal to. This is equal to twice the time period of red color, red source oscillation. And what is this point here? This is twice the time period of blue color oscillation. So now you have to look at resultant here. So when red color amplitude is 0, blue is not 0. Hence the resultant amplitude is not 0 here, is not 0 here. When is the resultant amplitude becoming 0? Can you identify when is the resultant amplitude is becoming 0? When red color oscillation and blue color have to be in the opposite direction. It is becoming 0 for the second time, somewhere between the two. So this is twice the time period of resultant oscillation. So what do you understand from here? The resultant oscillation, one more important point we can understand. Even the resultant oscillation time period will be somewhere between the two time periods. It will be average of the two time period. Hence the frequency of resultant oscillation. There are two things. I'm talking of frequency now. Amplitude is different, frequency is different. What is the frequency of resultant oscillation? I have not taken here because they're too close to each other. I have taken two time periods here. So if you observe, this is the time, this is equal to, this is the time where, again, this is the first time, again, resultant oscillation is 0. This is the second time resultant oscillation is 0. So this is the time equal to twice the time period of resultant oscillation, which is in between the two. It will happen after the smaller time interval, but before the second time, larger time interval, average time interval. The frequency of resultant oscillation is somewhere between the two. So I hope this point also understood. This is an important point. We'll come to mathematical derivation last. So what I'm going to do today, I think basically, I'm just trying to understand the beats in a logical way. And after we are understood in a logical way, then only we'll go to mathematical expression. The mathematical expression doesn't give a very good understanding. So if we understand all the points what we discuss here, this will give you, hopefully, it should give you better understanding of what beats is. Right. Okay. So what happens? So basically, we talk about this.
Sir, could you repeat the last point again?
Last point again. Okay. But let me repeat the last point again. Okay. So. There are two oscillations, blue color and red color. I have shown is the time period of both same. Time period is both not same. How do we measure time period? Time period is this is the point where phase is 0, and this point again phase is 0. So time taken from phase 0 to again 0 is the time period. This is the time taken from phase change to 0 when it achieves next 0. That's a time. It's a time period. One full wave is one complete oscillation. This is two oscillation. So this is a time where red color has completed two oscillation. And blue color also, this is a time when this is a time blue color is taken to complete two oscillation. Is this clear?
Yes, sir.
Now this is, so I write left one as right as 2 into TR and right one is 2 into TB. So this is a time period. Two of them are time periods are not same, which is makes logical sense because the frequencies are not same. Now, if I have to find out when is the resultant oscillation becoming 0? When is the resultant oscillation become 0? Two oscillation, red and blue have to be in the opposite direction and equal. If I draw a line somewhere here, is this not the times when resultant oscillation becoming 0?
Yes.
Why? Because one is positive direction, there is negative direction. So what is the, so if I want to understand what is the time period of resultant oscillation, I can understand resultant time period of oscillation is between the two time periods. Is that making sense?
Yes, I understand.
Understood. Good. And this is something intuitively it makes much more sense. Okay. Does anybody else any question?
Sir, I have a doubt.
Yes.
Sir, so that is the point where the first destructive interference occurs?
No. Destructive, you tell me in the figure where is the first destructive interference occurring? When is the first destructive interference occurs? Tell me when would the first destructive interference occur?
Like the phase difference should be pi, right, sir?
See, destructive interference is not a particular instance. See, just yes, this is the point. This is close to the time period where the destructive interference occurs. Are you following? So not only it is 0 at this time, it is 0 at this time, also it is 0 at this time, also it is 0 at this time. The complete full oscillation is wiped out. Are you following now?
Yes, sir. So then we say it's in destructive
Yes,
interference.
and you
Not
understood
just a
difference?
point.
Complete
Yes.
oscillation. If you take the complete oscillation is entire
Yes.
time period, there's no displacement. Are you understanding? This is the point where destructive interference is taking. This is the half the time period of oscillation of intensity. What is this point here? Vignesh, what did they say? What is this? What is T by 2?
Half the period of oscillation. So, but I didn't understand how.
Okay, what is the time period? Not oscillation. What is this one? See, there are two types. There's one frequency of oscillation. There's a frequency of amplitude. There's a frequency of intensity. You understand what does frequency of intensity mean?
So, like the time between one zero intensity and the other zero intensity.
You know, how do we find those two intensities becoming zero? Okay, let's continue further. So what happens typically frequency when we talk, even suppose I point t is equal to, this is time in seconds. Even if I take t is equal to 0, and if I plot t is equal to 1 second also. Even typically with sound source, as I mentioned here, I took 440. 440 is musical instrument. Most sound sources, what here is 200, 300 frequency. It means if I truly plot an oscillation, how many such complete wavelengths will be there? There will be some 200, 300 wavelengths. It may look something like this, even for 1 second. So this is something, is a kind of oscillation. Actually, it may look like. Okay. So earlier because we have just elongated, even for time is equal to 1 second, there is so many oscillations which are happening. Let's take another oscillation as superimposed another red color oscillation, which is a slightly different frequency. I hope you understand here. So what I notice here, this is the time where there is in constructive interference. When do you find, and you notice here, look at the peak here, crest values, slight gap is keep coming. So this is something gap will keep increasing as we keep along. So phase is changing. We find somewhere here, I find here, these two waves are opposite in phase. This is the point. So this is the time corresponding to destructive interference. This is the time corresponding to constructive interference. And whatever time you notice here, again, you know, where has constructive interference come here? Again, I notice here the two levels are perfectly overlapping here. So somewhere here, again, it is back to constructive interference. This is what I again was talking about maximum intensity, minimum intensity, again, maximum intensity. And in between, what will happen? Intensity will be something like this. So if I plot intensity, intensity will vary something like this. It will drop to 0, again drop to maximum, something like this. It will oscillate, and that will be the time. Okay, I hope this also is coming from there. So if blue color, let's take understand in terms of some number. So sometimes number gives us a better sense. If blue has angular frequency, angular speed of 800 pi. What is 800 pi? What is the frequency? If angular speed is 800 pi, frequency is 400. Now this is, so it will have 400 complete wavelengths in 1 second. And red color is 808. So this has frequency of 400. And this has a frequency of red color 404. So there's slight difference in frequency. And if you plot this out, the resultant oscillation will look like this. And both of them is equal to 0. By choice of time, we are taken to be together. Okay. So two oscillation at the position of observer will again be in the same phase and undergo constructive interference when the phase difference is equal to 2 pi. Is this understood, making sense? What will happen? The phase difference, see, this particular case, phase is changing faster. If t is equal to 0, what is the phase value equal to? Omega t. So this will be equal to, at time t, the phase angle of this will be equal to 800 pi into t. And this will be equal to 800 pi into t. So this phase will always lead phase of this. Phase angle will keep increasing. But when the phase difference becomes equal to 2 pi, it means they will again overlap. So when would oscillation at the position of observer will be again in the same phase and constructive interference? When the phase difference is equal to 2 pi. Yeah?
Yes, sir.
Have you understood this point?
Yes, sir.
Or you want me to repeat again?
No, sir, I understand.
So basically what I've written at time t. At time t, what is the phase of first one? Omega 1 into t minus omega 2 into t. And if the time is such that phase difference again becomes equal to 2 pi, it means is this the time at which again they will come in phase. And which the time, where is the time? This is the time t. They're again in phase. You notice here? So it was in phase here. Gradually it has gone out of phase angle, and you notice here gradually the phase difference is increasing. Phase difference has become 180 degree. As it increases from 180 degree further, actually angle between the two becomes smaller, and here again phase difference become 60, which is again in phase. So this is the time. This is the we are using it here. We are trying to understand how would this t depend on omega 1 and omega 2. We substitute t is equal to 2 pi. What we find here, after time interval of 1/4 of a second, again I'm seeing a constructive interference. So if I plot these two colors at t is equal to 1/4 second, what I find here, again there's a maximum. So what is the time period of what is the time it takes from one constructive interference to next constructive interference? It has taken 1/4 of a second. That comes from directly from this calculation. Okay, basically, if it is taken 1/4 of a second, again in next 1/4 of a second, it will reach a constructive interference. It means intensity is varying with the time period of 1/4 second, or intensity is varying with the frequency of 4 seconds. And what is that 4 second? 4 second is nothing but difference in frequency. Difference in frequency of the two source. So when this source has frequency of 404 and this has frequency of 400, it means intensity also will vary periodically with the frequency of 4 or time period. So in a second, 4 times it will reach a peak and 4 times it will reach a minimum intensity, or so intensity will vary. I hope logic behind this also, intuitive logic also is understood. 4 seconds. And this is how it is plotted. And this is the figure you'll find in almost every book. So what they write here, this is something, so if we draw, if there are two waves drawn here, what we notice, let's look at this point here. This also like oscillation, which is slight difference in frequency. So at this point, both reach their crest at the same time. So this is phase of both these waves here is equal to pi by 2 here. And again, what you notice here, when you come at this point here, as we draw vertical line, if we draw any particular instance of time, any vertical line will indicate a particular time here. At this particular time, this crest coincides with trough. So during this time interval, waves will completely cancel out each other. This is out of phase. And from here, whatever time it has taken out of phase, if it is out of phase here, if I take resultant amplitude, resultant oscillation becomes 0. So how would resultant wave will be? Here, maximum amplitude. So we know when we look at the frequency will remain same. This is a frequency. This is the time period. But amplitude is changing. Here, maximum amplitude. Here, 0 amplitude. Again, if I draw a vertical line here, I find this point and this point are in phase. Amplitude becomes maximum. So this is how the resultant wave will look like. The resultant oscillation. This is the, when I take this oscillation from this time to this time, this indicates time period of oscillation, or inverse of this time period is frequency of oscillation. And this time to this time indicates time period of intensity, variation of intensity. Inverse this time gives you frequency at which, as we have seen in previous case, frequency at which the intensity is varying, which is called beat frequency. How much is beat frequency? Beat frequency, as you've seen before, is equal to difference in frequency. And what is this frequency equal to? This frequency is average of the two frequencies. So if at all want to understand, those who are not understood anything about the beats, what is the result conclusion we come to? That's the resultant conclusion here. What is the resultant conclusion here? What are the two most important characteristics of sound? One thing we call as pitch in general terms, which is nothing but frequency of oscillation. And second thing, loudness. which measure in decibel, which is measure of intensity or amplitude. When we have resultant of two sound waves of nearly equal frequency, F1 and F2, what will the frequency will observe and what is the intensity will observe? Okay, so what we observe here, that's what our basically we are coming to conclusion of whatever we had discussed so far. Resultant of two sound waves of nearly equal frequency. I have to define two things. What is the frequency of oscillation, or frequency of pitch of the sound I'll hear, and what is the loudness of sound I'll hear. The frequency will be average of the two frequency, F1 plus F2 by 2. Like previous case, I have taken two frequency 400 and 404. If two frequencies are, for example, as we see in this case is 400 and other frequencies 404, what will happen? The sound what we'll hear will sound like a sound of frequency 400. And intensity will vary, sorry, not amplitude, not as intensity. Loudness is better measure. It will vary with frequency equal to difference in frequency. The wow sound wise, how many times will go up and down? It will go up 4 times in a second, F1 minus F2. So here, if those are 400 and 404, what would from this time to this time will be equal to? This time interval will be equal to 1/4 of a second. And what is this time from here to here is equal to? This time is equal to 1/402. Now coming to, okay. Two waves of same amplitude. What causes beats? Now we'll mathematically, okay, sorry, I think I didn't know that. I thought it's 11:30. So I'll stop here. I will take it up in the next session. So next session, as today we had more of a